We are going to show some gory details here so that we don't have to do it again. And then you'll see that the gory details are inherited by R, which is a vector space you've worked with your whole life. So I just want to remind you that everything is really getting the properties. All these vector spaces we're going to talk about have underlying it. They're all built on R. So the big idea is that a general vector space has two operations, addition and scalar multiplication. And for those two operations, it is closed. Okay, and we'll talk about that again in gory detail. And then it satisfies these 8 properties that we've talked about already, but these are the 8 properties. Okay, so we're going to start out by just reminding ourselves that what we've been doing all semester, Rn is a vector space for n equals 1, 2, 3, and so on. Okay, so now we're just kind of generalizing. We're going to talk about some spaces. We're going to call them vector spaces, but they basically have the same structure as these Euclidean spaces we've been studying. So we're just going to go through some examples. Right now, we're just going to go through this example right here. So it's the set of all 2 by 2 matrices, and all of the elements, all the entries in the matrices are real. So again, we're going to see that this has all the properties of a vector space because it's built on R, because all of its entries are real numbers. Okay. So first we're going to just show that the 2 by 2 matrices, that whole set of all possible 2 by 2 matrices is closed under addition. So whenever you're trying to show closure, you just do this. You say, okay, I'm going to take 2 elements that are in my set, and I'm going to show that their sum is also in my set. Okay, but what you do, and it's kind of probably not going to seem that interesting to you, but it's like what we did when we showed closure for subspaces. So you take an arbitrary element and you just write out what it looks like. So we're saying A and B both just look like 2 by 2 matrices with entries in R. Okay, so this, and I'm going to write, again, the gory details, but we're not going to write it probably this gory with details again, because you'll see that it just takes a lot of time and it's not that exciting what we're doing here. So, but it's important to understand this is where you get all the structure. So basically we're just saying that they both are 2 by 2 matrices, their entries are in R. Then we know also that if we add them up, we know how to add 2 by 2 matrices. So we're just going to do that. So we write out each one. I'm going to, again, this is a little gory in the detail, but in case anybody's a little confused about how this works, you will now see it. And then you'll see that showing something is closed under addition is this straightforward. So it just says, okay, when you add 2 matrices, we already know that you add them entry by entry. So we get A11 plus B11, then we get A12 plus B12, A21 plus B21, and then A22 plus B22. All right, so now all we have to do is observe that this thing is in R 2 by 2. And the whole reason is that each one of these entries by themselves are real. And the reason they're real is that R itself is closed under addition, because we know that if we took this element that's real and this element that's real, then its sum is real. Okay? So then the same thing for all 4 entries. So this is in R 2 by 2 since the underlying R, all the entries, is closed under addition. So basically that's going to be the main, if something works, you'll see that it's going to work out because of the underlying properties of the reals. Okay, so now we're going to show that this thing is closed under scalar multiplication. So again, the same strategy, you just take any scalar, so any real number, and you take any element in your set. So in this case, it's just a 2 by 2 matrix. Then we know, we already wrote out what A is above, so then we know K times A is just equal to K times, and then we just write the entries of A, A12, A21, A22, and then we know that scalar multiplication works with matrices as you just multiply each entry. So we get Ka12 and then Ka21, Ka22. All right, and then you'll see that this is inside it's a 2 by 2 matrix with entries in R, since R is closed under scalar multiplication. So you might think it doesn't feel like you're really doing much, but you are showing these 2 closure properties, which are really important. So all the entries are scalar times a real number, so we really did need to use that R is closed under scalar multiplication. Okay, so now we're done. We've shown that our set is closed both under addition and it's closed under scalar multiplication. All right, so those are the 2 main things, and these are back in the definition, that we have a set, and it's got to be, basically just says here, if F and G are in V, then so are its sum, closed under addition. If F is in V and K is a scalar, then the scalar times F is in V. So that's closed under scalar multiplication. All right, and then we have these 8 properties right here. So we're just going to look at these properties one by one. And again, this is more gory detail than we're going to do in any other examples, but just so you see the big ideas. So the first property is if you have these 3 elements in your set, then it has to have be associative when you add. So we already set up what A and B are, so now we're just going to say C has the same structure. So we're going to say that A plus B plus C is equal to, and again, A11, A12, A21. And we're only using these indices because then we don't have to make up too many letters because we have so many variables here. So B11, B12, B21, B22. And then we're going to add those first. That's what the parentheses mean. And then we're going to add C. We're not adding yet. C11, C12, C21, C22. Okay, so the parentheses say add these first. So again, we know how to add 2 matrices. And then we're going to add the third one. And then we know how to add. Now we basically have 2 matrices again, so we're just going to add. So we got A11 plus B11 plus C11, and then A12 plus B12. So what you're going to notice here is, again, the underlying operation is that R itself is closed under, it has the associative property for addition. So, and then finally, A22 plus B22 plus C22. And then the idea here is now we're going to unpeel it. We're going to unpack it so that we have A by itself and B plus C. So we're just going to peel off the A. And when we do that, you'll see we get A11, A12, A21, A22. And I guess I should really emphasize why we're allowed to do this. So here we're just adding matrices. But in this step right here, I guess I could write that step in. And then I think what I'm going to do, I might not go through all 8 of these properties. I might then just, so I'm just going to show you that this is equal to, sorry, I'm going to do this. A11, I'm basically using the associative property for R. And then the next one is A12 plus, and then B12 plus C12. And then A21 plus B21 plus C21, and finally A22 plus B22 plus C22. All right, so now that tells us that we can unpeel it, unpack it. So we got A by itself, and we have B plus C together. So this is showing us that associative property. But you'll see the book doesn't bother to do this because it's so much writing, and it makes it maybe seem more complex than it is. But the take-home message that you want to remember is that the underlying structure is because R, the real numbers, have all these properties that we are showing that our vector space has. Okay, so that was the associative property. We could do the exact same thing to show that matrix addition is commutative. And again, I'm just going to post this in the notes, so I'm going to have that written down if you want to see the gory details. We're going to also show there's a neutral element. So this one's important. This neutral element, the additive identity for matrices, is just the 0 matrix. Okay, so what we're going to see is if you take any matrix and you add to each element 0, you are going to get back the matrix itself. Okay, and again, this is the underlying property that 0 is the additive identity for the real numbers. And so we know right here, when we add 0 to any real number, we get back the real number. So that's why the 0 matrix is what the neutral element is here. Okay, and then you'll see that this is just A. So that shows us that if we had A and we add 0, we just get back A. All right, so that's the additive identity. And then the additive inverse, same idea. We're basically going to use the fact that A has all these real numbers, and we know that each real number has an additive inverse. and the additive inverse is just the negative of the real number. So when you put that together into a matrix, you'll see that you just take the negative of each element, and you're going to get, when you add those up, you go term by term, you get A11 minus A11, and then A12 minus A12. And this probably seems obvious to you, but again, this is just so that you understand that we're just getting all these properties from R. Okay, and then when we do that, we get back that neutral element, which here is just 0, 0, 0, 0. All right, so B, the additive inverse, is actually negative of A. So I'm just going to put this, B is equal to negative A. Or if you wanted to think of it term by term, each term has a negative. All right, and so we are almost done. So then there's also this property which says that if you take a scalar and you multiply it by the sum of two matrices, then you're going to get the scalar times the first matrix plus the scalar times the second matrix. So again, I'm going to write that one up. I'm not going to go through it right here. Same idea here. Now if you take the sum of two scalars and you multiply them by a matrix, then you're going to get the sum of the first scalar times the matrix plus the sum of the second scalar times the matrix. Okay, and then almost done, you take two scalars, and if you multiply one, and then first you had multiplied the second one by the matrix, so you take the scalar times the matrix, and then you multiply the second scalar by that product. Then you're going to get the same thing as if you just first multiplied the two scalars and then multiplied them by the matrix. So we're going to, again, I'm going to post that. And then finally, if you take a scalar 1 and you multiply it by a matrix, you're just going to get the matrix back. So that's going to be it for this, and then I'm going to post a bunch of examples.